So that's what we're going to do. So what's today's date? 9/10. So we've spent class to this point discussing what we'd call applications of the integral. And so what we're going to do now is we're going to move in a slightly different direction. It's not that we don't want to do applications. It's just that one of the things that we've learned in doing this is that there's a lot about integration that we still haven't sort of covered. So in doing this, we've encountered some integrals we didn't know how to compute. And so what that means, that's not necessarily good, well, if we want to transition into the right thing, what that means is there's something about integration we still don't know, in the sense that the amount of functions that can be integrated, if we put them in a room, theoretically speaking, the ones that we actually know how to do at Calculus 2 right now would maybe fill up a garbage can. There are lots of integrals we don't quite know how to compute. And so we need to figure out how we can sort of do that. So let me remind you of some of these. So for example, we came across this integral. We came across this integral. We came across this integral. And something like this. So maybe so these guys require some trick, and I'll put it in quotations because it's really not a trick, that we haven't learned yet. So what we need to do is we need to sort of work on our integration skills. So that's a good way of thinking about this moving forward. We are very unskilled when it comes to integration. Now, of course, the argument you might have is you might say, well, that's great. Who cares if I know how to integrate, because software can do it for me. And I'm not necessarily disagreeing with that. That software can do it for you. I know it can. What I will disagree with is that you still need to learn these techniques, because you're missing the point. The point isn't for us to be able to compute an integral. The point is, that obviously that I misspoke. You should, in this class, you have to prove that you can integrate. But if you're thinking of a practical purpose moving forward, the point is not so much that you have to do complicated integrals by hand. The point is that you know what the integral represents, where it comes from, and perhaps more importantly, you need to understand the theoretical aspects of this. And we sort of touched on that. Maybe theoretical is a bad way of saying it, but sort of the construction of these things. How can we use these bigger ideas to solve new problems? So with that said, we're going to do that. So for the next few classes, we will learn new sort of techniques of integration. To go along with the one we already know. So what is the only sort of technique that we've learned so far? That was the change of variable. Which is also known to amateurs as U substitution. So one thing you might ask or you might question is how do we develop sort of new tricks, or how do we develop sort of new formulas, and why would we develop them? What are they good for? Well, there's lots that we can say about this, and there's lots that you might learn in here. There's lots that some of you will learn in courses after this. But for the sake of argument right now, let's just sort of digress back to what the integral, what these symbols actually mean. So we already discussed, and this is something that was hit on in Calc 1. It's something that we've mentioned before. So don't forget that when I write the integral of f of x dx equals gx plus c, don't forget that that is an equivalent statement to the fact that the derivative of g equals f. So this goes back to these words like antiderivative and derivative. And if we sort of ponder this a little more, we might say, okay, what was the change of variables theorem? What did that come from? That is an integral statement of a property of a derivative. And what it was is the change of variable, or the U substitution, how that worked is we were sort of undoing what we call the chain rule from calculus. So in Calculus 1, we learned this thing called the chain rule. It allows us to differentiate the composition of two functions. And what happens is we recognize that that pattern of differentiation using the chain rule can in many scenarios be reversed, provided we make an appropriate substitution. So we're not going to go back into that because we've done that now in not only this semester, but in Calculus 1. But the point I'm trying to make is you might ponder to yourself, okay, if we use the chain rule to our advantage, what other rules did we have in calculus that might be of use? And if you think about it long and hard, you remember, okay, we had this rule called the sum and difference, but that's kind of an elementary rule. we had this thing called the product rule. So the question we might ask is as follows. So let's sort of make a note. So the change of variable technique was derived from the chain rule. So we might ask, what can we derive from the product rule? Now you could say, what about the quotient rule? Well, turns out there ain't a rule for that. But there is something for the product rule. So as Zafalgar suggested in the chat, why don't we, if you go back to what we did in Calc 1, we wrote the chain rule down in terms of derivatives. And then what we did is we rewrote it in terms of integrals. Just like on this previous page, this line in terms of integrals is equivalent to this line, which is written in terms of derivatives. It's two ways to write the same thing. Ryan is older than Shobit. That's a true statement. Let me rephrase it another way. Shobit is younger than Ryan. That is two ways to say the same fact in English. So what we're saying here is this, on this page, we have two ways of writing the same fact about the relationship between f and g. One is in terms of integrals. The other is in terms of derivatives. And so what we're asking is, what happens if we take the product rule and try to write it in terms of integrals? What do we get? And then not only what do we get, is it useful? So let's recall the product rule. What does it say? Well, it says that the derivative of the product is expressed like this: f prime times g plus f times g prime. Now I'm using some shorthand, but the point of the formula is what's going to matter, the structure of it at least. So this is called the product rule. This is how we differentiated products. So what we want to do now is we sort of want to say, can I write that in terms of integrals instead of derivatives? Or another way of saying that, what happens if I just integrate that whole equation? How many terms do you see in that equation? You see three terms. There's one on the left and two on the right. So if we quote unquote integrate, so we can integrate and apply the fundamental theorem of calculus. And what that means is that means the derivative and the integral are inverse operations. Right? So if I do that on the left-hand side, the only thing that survives is, well, let's just write it all out. So on the left-hand side, we have d dx, and we'll put the arguments in here right now just because it might be a little easier for us to follow along. So I'm going to use prime notation. So if I integrate both sides now, so I'll put that in blue. I'm going to integrate with respect to x on both sides. On the left-hand side, the derivative is undone by the integral. So all that survives on the left-hand side is f of x times g of x. And then on the right-hand side, I'll write this as two integrals. And now what I'd like to do is I'm going to solve. So let's rearrange. And I'm going to rearrange it as follows. And it might not seem to you why that's useful, at least not yet. And I'm going to use what you guys are familiar with, the commutativity of multiplication. Like 4 times 5 is 5 times 4. So I can write this, I can switch these two terms. So this particular formula is extremely, extremely useful. It has a name, which we'll tell you in a second, and then we'll explain why it's useful. Before we do that, does anybody have a question or a comment? Let me reiterate that the reason there is no longer an integral on the left-hand side at the second line is because I had a derivative there. And if you integrate a derivative, you get what you start with. So it's not precisely the same idea as this, but perhaps you'll get what I'm saying. If I suppose I had the number 5, and then if I square it, I get 25, and then if I take the square root, I get back what I start with. So you can think of the derivative and the integral as sort of behaving in this way of operating as an inverse. Questions? Now, this looks like a big mess of a formula, but it's saying something if you look at it from a different perspective. One of the issues we always have, especially in math, and that's because it's scary looking, is we fail to see that there's some beauty hidden. And what's beautiful about this formula is that even though it looks sort of overwhelming, it's telling us something. And so what is it telling us is it's telling us that there might be a scenario where we have an integral. And we're not sure how to write it. Or excuse me, that's a bad way of saying it. We're not sure how to determine the integral, to evaluate it. However, if we recognize that the integral we're stuck with has a particular form, then we just might be able to write it as something minus another integral that we do know how to evaluate. So let's make a point to say that on the next page. So So this formula, the integral, excuse me, I wrote it wrong. So the formula, the integral of f of x times g of x, its derivative dx. So I'm just copying the formula that was in the red box down again. This is called the integration by parts formula. Now, this creature is extremely useful in all types of areas of mathematics. Not just practical applications, but theoretical things in math. It shows up in many, many places. It shows up in places well outside of math, where math shows up, like things like quantum mechanics and quantum physics. And, I mean, there's endless places this equation shows up and is useful. And there's so many things that we couldn't even begin to sort of say them all in this class. However, what we can ask in this class what it's useful for. Why is it useful to students studying elementary calculus? So why is it useful? Or to us, what good is it to us? Well, hopefully, we can use it to write difficult or unknown integral equals expression minus known or easy integral. So when the way I've written this silly thing at the bottom in blue, compare it to the purple equation up top. The integral you want to know might be unknown, might be difficult. And what this formula says is that if you're creative enough and the integral is of the right form, you just might be able to write it as this expression, f times g, minus the integral of g times f prime. Does anybody have a comment or a question? Now, we're going to show you how to use it in about a minute. But before we do that, we need in most textbooks, once they derive this formula, it's often easier to use if you sort of shorten it a little bit. And we're going to do that in about 10 seconds. All right, so let's make a note of that. So it's useful to use a different notation when employing it. So what I'm going to do is I'm going to set u equal to f of x and v equal to g of x. So this is not a substitution like we did before. We're using a shorthand notation. So, and then we're going to use these things that we called before. We talked about this very briefly in Calc 1. We called these things differentials. So what is du dx? Well, you can write du as f prime of x dx, and dv is g prime of x dx. So you've done this before. This is how you did your substitutions. You would set like u or y, and then you would rewrite the du's or dy's like this. So what does the formula become? Well, it's a little easier to memorize and use when we write it like this. So the integral of f of x g prime of x dx equals f of x gx minus the integral of g times f prime of x dx. Well, let's look at what all these symbols now mean. This guy is just dv. This is just v, and this is just v. And then this guy is u, this guy is u, and then this guy is du. So what this becomes is a little easier to memorize and use. So it becomes the integral of u dv is equal to uv minus the integral of v du. This rolls off the tongue a little easier, and it's also a little easier to use. So there's a lot happening here, and I know we spent about a half an hour going over it, but we're going to start doing some problems now. Anybody have a comment, question? So what's nice about this formula is it kind of gives you sort of like a procedure to do this. If you want to use this formula, you got to find a u, and then you got to pick a dv. And then once you choose a u and a dv, you want to choose them so that the derivative is quote unquote a simpler function, but you want to choose your dv so that its integral v is simpler. So let's get right into it, because that way it won't be so overwhelming that we've written all this crap down. Okay, so let's do some examples. We'll do one in great detail, and then we'll do the other ones in a little quicker. So let's integrate x times the cosine of x dx. This will be our first one. So here's what I'm thinking as someone who has experience. Anytime you have a product of a polynomial and a trig function, anytime you have the product of a polynomial, x is here, that's a polynomial, it's a very simple polynomial, it's a polynomial, and a trig function, one of the first things that you should attempt to do is a substitution. Excuse me, substitution. Of A, now. Parts. So here's the idea. So the product x cosine x suggests trying parts. Now, experience tells you what's a good try for you, and experience tells you what's a good try for DV. But if we think about this from a logical standpoint, we know that if we take the function x, y equals x, or in this case, u equals x, if we take its derivative, it's no longer, it's now a constant, it's 1. That simplifies, we would think, right? Whereas if we had to integrate x, it becomes 1/2 x squared, which makes us think it becomes more complicated. So what we'll do is we'll choose, let's choose u equal to x, and I'm going to choose my dv equal to cosine of x dx. So notice how I did this. My u is just a function, but my dv is technically a derivative. So I have to write it in this differential notation. I have to say dv equals blah. Okay, so if that's the case, then I need to find du. What is du? Well, du is the derivative of u. But we must use the differential notation. So this says that du is equal to 1 times dx. And then what is v? Well, how do we undo the derivative of v? We integrate. So v becomes the sine of x. Now, at this point in calculus, you need to be able to mentally integrate cosine. That should not cause you great stress. And if it does, then, you know, I hate when I say this, but it's true. You're doing calculus wrong. If at this point you have to know certain facts, just like you know that 2 and 2 is 4. You just have to know. Now, of course, we're not going to just write du. There's no reason to write 1 times dx. So remember, whenever the constant is 1, we just sort of omit it. So we'll just write du equals dx, which is the same thing as saying the derivative of u with respect to x is 1. It's the same thing. So now we're going to plug them into the formula. So I think a good way of learning this and to help you recite it numerous times so that it becomes memory, you don't go home and make flashcards. Or I mean, I guess you could, but I think the best way to learn this is to recite it and recite it when you're using it. So here's how I would encourage you to do this. The integral we started with was the integral of x cosine x dx. And we know that the formula says that if this is u, and this is our dv, then we know that this is uv minus the integral of v du. And so now we just plug them in. What is u? That's x. What is v? That's sine of x. Minus the integral of sine of x. And then du is just dx. And so you're going to see why the integration by parts formula is so useful. If we look at this, we went from an integral on the left that we didn't know how to compute, and we've reduced it. We've reduced it to something we do know. What we do know is that the integral of sine is negative the cosine. And so this becomes x sine of x plus the cosine of x plus c. And we're done. So here's the cool thing about practice. If you practice these, you'll start to notice lots of themes. Like anytime you have a polynomial times another function, setting u equal to a polynomial is usually a good start. It will often work. Does anybody have a comment or a question about this? Let's do another example. This one is almost identical. What is the integral of, say, x e to the x dx? So once again, I have a product, and I have one that's very easy to differentiate, and technically both are very easy to differentiate, as in the previous one. But one of the functions' derivative becomes simpler than its function itself. You know, and that being in I guess in quotations when I say simpler. So here's what we'll do. We'll set u equal to x and dv equal to e to the x dx, so that du once again is dx, and v is just equal to e to the x. And then once again, the integral we're after, xe to the x dx, is uv minus the integral v du, which is xe to the x minus the integral of e to the x dx. And just as in the previous problem, the integral that we're left with is an elementary integral. Any comments, questions? Okay, so they're not always this sort of, I don't want to say easy, that's a bad word, but they're not always this quick. So some problems that I'm going to give you on homework, and then we can talk about them if you have. Questions. So sometimes an integrate or an integral requires multiple applications. Of the formula. So an example of that, which you'll do for homework, is this integral. This is, what if instead of what we did before, what if it's x squared e to say 5x dx? So now what happens is sometimes you get lulled into that there's a pattern. So sometimes we need to be creative. Yeah. So examples of this. We'll do one easy one, and then we'll do one that's sort of not so easy. So the first one we're going to do is the integral of the natural log. What function out there's derivative is the natural log? That's what we're thinking about here. So for this guy, you might say, okay, how can integration by parts matter here? You're going to say that all these examples that we've done in class, you've done 2 and said there's at least 3. you'll say, well, there's no product here. But in fact, there is a product here. You just aren't thinking of it as a product. Don't forget that the number one is always involved, right? So really, the number one is in here. So I think, Zafalgar, you pointed that out. There is a way to do this. So here, we're going to set u equal to the natural log, and we're going to set dv to just dx. So this doesn't sort of fit the pattern that a lot of the examples you're going to use. A lot of the examples you're going to have, you would never think of setting u equal to log. But if you think about it, it's your only option here. Because if you tried to set dv equal to the natural log, well, that would be redundant because we're already asking you what the integral. The problem is asking you what is the integral of log, the natural log, I should say. So setting dv equal to the natural log would be redundant because that's what the original question's asking. All right, so if we choose this, then what is our u? Well, our u is 1 over, or excuse me, log of x. So our derivative is, I'm losing my mind. U is log x. So the derivative is 1 over x dx. And v becomes the integral of 1, which is just x. And so the integral we started with, log x dx, which we know is uv minus the integral v du, becomes so u is log x times v, which is x, minus the integral v, which is x, times du, which is 1 over x dx. And so we can clean this up, make it a little cleaner, x log of x minus the integral of 1 dx, which becomes x log x minus x plus our arbitrary constant. So this is another important integral, and it shows a slightly different sort of pattern that you will see in many of them. Isn't this fun? Just think, 10 years from now, you're going to be able to say, I learned all this integration and my life is so much better now. You might be like in the back of an alley and some person comes up to you and tries to mug you or something, and you say, stop it. I know how to integrate the natural log. And of course they're going to run away because they're going to say, holy shit, this person is how to integrate the natural log. I better run. And your life is so much better for it. Questions, comments? You're allowed to ask anything. What the hell? That's why I miss people being in a classroom. We can't even talk about life. I have so many fun stories I can share, and none of you get to hear it because you're all sitting at home, sleeping. No one's even paying attention. Well, Zafalgar, at least you are. You've been chiming in. 10 points for you. Yes. Shobit has a question.
For the
previous slide? Sure. Yeah.
So you can, the example, right? The x squared and
yeah.
E power. So if I choose u to be e power 5x, right?
Yeah.
So dv will be x squared dx, right?
No. Choose u to be x squared. So Shobit's asking the question for this one. You're going to put, this is going to be on your homework, but I'll tell you, just to get you started, this guy right here, you're going to start with u equals x squared, and dv equals e to the 5x. And so your du is going to be 2x dx. Does that make sense? And then your v is going to be 1/5 e to the 5x. Now what's going to happen is when you perform the integration by parts once, your new integral is going to, instead of it being x squared e to the 5x, it's going to be x e to the 5x. So it's just going to be like the previous example. So that's what I mean by you're going to have to do the formula twice. And so that'll be your first parts formula. Then the next time you'll set u equal to x. Does that make sense? Someone else had something to say. I bet you they say I'm alive. I knew it. How did I guess, Emily? You were alive. Never would have guessed. Not necessarily that it was you that said it, Emily, but I always think if I were a student right now and I was Zooming, I don't know what I'd do. I'd probably be home playing, like, what games are out now? I don't know. I'd probably be playing the Xbox or pretending I'm paying attention. I don't know. Taking a nap, daydreaming. I highly doubt that, Zafalgar. I highly doubt that. Yes?
Can you remind me the formula you used
To get this?
Yeah.
Okay, yeah, that's a good question. So here's a sidebar. Before we do our next, actually, I'm glad you asked, because there's three things. I've mentioned these before, but it's worth noting before we do our next example. So thank you, Mike, for asking such a question. We'll give you points for, and it is Mike, right? Yeah, okay. See, I don't want to make sure I forget. What are you like? I ain't Mike. So the question, the question Mike was asking is if I go to this page, how did I get 1/5 to the 5x here? So here's three formulas that you should always sort of keep in mind that are very useful. So here are three useful facts. And why do I say they're useful? Because these three integrals pop up over and over again, and it's you don't want to have to think about it. I mean, you can think about them, but you want them to be something that's, again, something that's as quick to you as 2 + 2 is 4. So the first one is the integral of e. I don't care what number a is. In that problem, it was 5. The integral of e to the ax is always just 1/a e to the ax. Fair enough, there. That is good. Now everybody's going to start chiming in. I love it. You guys got the nerves now. You know I'm only kidding, right? I'm not like upset or anything. I know you're all just being shy. Okay, so that's, and you can verify this very easily, but if you want to see when I'm using it on the problem you asked about, Mike, what we're saying is the integral of e to the 5x dx is 1/5 e to the 5x plus c. And what I would encourage you to do is, instead of thinking about this as an integral, just differentiate the right-hand side and convince yourself that it's true. Now, of course, this doesn't work. Look, in all these problems, it's very important we understand this. Let me be very clear. A can't be 0, because then it doesn't make any sense. But if a is 0, then you're just integrating the number 1. So, as long as a is a number that's non-zero, this makes sense. All right, now we also have a very similar thing for sine and cosine. The cosine evaluated at ax, its antiderivative is always 1/a, the sine evaluated at ax plus c. And so if you're looking for something to compare that to, let's do a specific example. How about the integral of the cosine of, say, 3x? dx would be 1/3 the sine of 3x plus c. And then, as you may have guessed, there's one for the sine as well. It's very similar. Only there's a minus sign out front. And if you want to keep score at home with a specific example. So the integral of the sine of, say, 7x would be I forgot my dx. I'm going to start making mistakes you guys make. I'll be fired. So this is 1/7 with a minus sign in front, cosine 7x plus c. So knowing these things rapidly is going to be very time saving going forward. And again, I emphasize to make sense of these, just differentiate the right-hand side. That's one way to think about them. The other way is they're just basic substitutions. They're basic U subs. Yes.
What if the x is because I cube one is
Inside of there? I mean, like inside the cosine? No, you're not going to come across that. That ain't done in Calc 2. So the question was, what if you had something? I think this is what your question was. I think you were asking, what if it's something like this, like say the cosine of x squared? Is that what you're talking about? Oh yeah, it doesn't even matter if there's an a. This ain't happening in Calc 2. You ain't integrating that. Does that make, all right?
But there's a way of doing it.
Say that?
There's a way of doing it, right?
No, there's not. So the question is, can you even integrate cosine evaluated at x squared dx? No, not in terms of functions that you're familiar with. You know, just for fun, let's go to our friend. You want to go to visit our friend? Let's go to Wolfram. How that? Let's go see what Wolfram has to say about this. So Shobit wants to know how we do this. That's a good question. Where you see this cute stuff. Yeah, this ain't for us in Calc 2. So this is called a Fresnel integral. These show up in study of like wavelengths and optics and stuff like that. But this is not Calc 2 stuff. So if you want to know more what I mean, if I say, you can only write that integral in terms of other integrals. So a Fresnel integral is this. If you want to learn stuff, your head will explode. See, there you go. And look, I ain't even lying to you. What do you see? See, O'Grady doesn't just make crap up. Optics. Right? So the point of the matter is there's no elementary way of describing that integral. So you'll see down here, and we'll learn what this means later. One of the things we do is we write the integral in terms of what's called an infinite series. And we'll talk about that in a few classes. Yeah, this stuff is, you got to be careful. This is why I suggested, one of the downsides to Wolfram is if you guys use it and you don't know how you're using it or why what you're seeing. See, here's the thing about technology. This is actually a very good, I'm glad you asked this question. One of the problems is that especially amateurs, and we're all amateurs at different things. I'm not an amateur at calculus. You are though, right? But there's definitely areas of mathematics where I'm an amateur. And so one of the problems with technology is we often just use it without understanding what we're using. And you guys will do this because this is what some of you knuckleheads would do. I could easily put this problem on a test and you would just copy it off, the internet, you don't even know what you're writing down, right? So again, I emphasize this enough. If I go back to the Wolfram page, when you see things like this you don't understand, you should ask. So think about what the real world's going to want from you guys when you're working. Right? They're going to want you to, most of you at least, if I'm assuming you all be using technology in some way at your job, the job, especially of the mathematician and the engineer and the people who do this kind of stuff for a living, and maybe you end up not doing this, maybe, but I guess it's the same thing with chemistry and biology too. If you're sitting around putting things into a computer or a machine and that software or that machine is giving you information out, you need to know how to interpret what they're giving you and how to make sense of it, right? So I can easily put this on a homework as a not a joke, but just to see what you'd write, and almost every one of you would write something like this, having no idea what it was, right? And that's okay. But that's the downside to technology is we use it often without understanding what the technology is telling us. And so one of the skills that, I think is important, and I would imagine people who want to hire you over the next few years and going forward, that they're going to want people who not only know the math and the science, but they want people that know how to plug it into some machine or computer. And they want to know that the person who plugs it in knows what they're plugging in and knows how to interpret what's coming out. And then, of course, when something gets spit out of the machine that we don't know how to interpret, we need to learn how to figure out what it means. Now, I'm not suggesting you need to know what the Fresnel integral is in Calc 2, because you don't. Some of you will get to learn about it in some maybe engineering classes or other math classes. But all this is doing is it's just writing this. This is just shorthand. What you're seeing right now in Wolfram is shorthand for an integral. It can't write it any cleaner than square root of pi over 2 times an integral. That's the best it can do. Now, if I ask it with bounds, say I say from 0 to 1. Now it's just going to spit out another integral. This is shorthand for an integral. Then it gives me an approximation using like a Riemann sum or something. And we'll show you how to do that soon enough too. Does that make sense? So yeah, there you go. That's a good lesson for today. Learn how to use technology. That's hard to do, right? I always find it disingenuous when people, especially instructors, aren't honest with you. I mean, there are engineers working right now that are sitting around doing this stuff by hand when they don't have to, right? You're going to want to use technology to assist you, particularly when you're doing computations. Because one thing is, if the software is reliable, it's not going to make the same errors you might make, provided you give it the correct information. And so that's an important skill. All right. Does that make sense? Okay. All right, let's do one more example. Oh, someone's asking something. TGX dx, what the heck does that mean? What is TG, Zafalgar? I don't even know what you mean by that. You have to be more specific. Oh, the tangent. Well, tangent's easy. The tangent, we just do what? We use a U substitution. So, Zafalgar, you're asking about the tangent. By the way, let me say something, because this, while we're on it, and I know this isn't what you said, but it's worth pointing out. So this integral that we just did here, the log x dx, this guy, I'm not going to do it. I'll ask you to do it on your homework, but the integral of the arctan x dx is done similar to this integral. What you're going to do is you're going to set u equal to the arctan, and you're going to set dv equal to dx. So we'll put that on the homework. You'll probably have questions. That's okay. So Zafalgar, you asked about the tangent, and I'm not going to do it, but I'll just show you how to do it real quick. The integral of the tangent of x is the same thing as the integral of sine over cosine. So this is a change of variable problem. So I'm going to set y equal to cosine and dy equals sine x dx. And that just means that the integral of sine x divided by cosine of x is just the integral of, oh, excuse me, there's a minus sign here. this just becomes minus the integral of 1 over u du, or excuse me, 1 over y dy. Which becomes negative the natural log of y plus c, which is negative the natural log of the cosine of x plus c. I don't know. How can you do it by parts? You probably end up getting it. If you do it by parts and you take, so when the derivative of tangent is secant squared, then you end up getting x times secant squared. I don't think that's an easy integral, at least for the tangent. You could try it. Maybe you get somewhere, but I don't think, so the question was, can you integrate tangent by parts? And I do not believe that it's, if you can, it's definitely not going to be straightforward like this. Any other questions? Comments about these examples? All right, so our last example is going to be, it's a famous trick, and it's different than all the other ones, and it's challenging. I think this is our fourth one, right? Yeah. So what is the integral of e to the x cosine x dx? So this guy requires two integration by parts. And it's not obvious why this will work, but it does work. And so it helps to call, I'm going to give this integral a name. I'm going to call it I. Just so I don't have to keep writing it down. So this is an interesting example because what we're going to do is we're going to do two integration by parts, and we're going to end up with an equation where the unknown is I. And so we're going to use some pretty cool reasoning to figure out this integral, not by computing it directly, but by writing it in two different ways and determining an equation for it. So this is a very interesting sort of problem. So the trick is to get an equation where I is the unknown. And then we can solve for it. So, you know what? It's 3:13. We're supposed to be done in 2 minutes. So we're not going to have enough time to finish it. So maybe you guys can try it on your own, and then we can finish. We can do it tomorrow. Yeah, right. So it turns out, Zafalgar, you can use u equals e to the x, but you can also use u equals cosine in this problem. It's not going to matter. What will matter is what you do with the second integration by parts. So try it. It's a famous integral. It actually pops up in lots and lots of applications. So give it a whirl. It's not going to be complicated. It's the same exact length both ways. The only difference is by taking u equal to cosine first is you get a negative sign in there right away, because du would be minus cosine. But it's the same process both ways. And you could verify that for yourself. Anyhow, we'll do it on, and it's more or less, to be honest, Trafalgar, it's personal preference, which you want to use for you. In this problem, in this one. Not in all, but in this one. All right, we'll get on this tomorrow. Thank you guys very much. If you have questions, let me know. Otherwise, I will see you, or at least you'll hear my voice and see me tomorrow. Oh, yeah, what would tomorrow be? That's a good question, Eric. So, I mean, honestly, there's enough people that don't come in person. You guys can probably all come. Yeah, technically tomorrow's Group B. How about this? Group B is supposed to meet tomorrow. So if Group B is official, but if you were in Group A and you want to come in person, come in person. There shouldn't be any issues. All right? Is that okay? So even though it's Group B, technically, if you want to come and you're in Group A, come. All right? I'll put that in an email tonight or something, just so everybody knows. More people don't come than come, so there should be room if you want to come. All right, guys, thank you very much. Have a good weekend. Well, hopefully you'll join us tomorrow. Thank you, guys. I appreciate it. See you tomorrow.